Thank you. If you would recall, yesterday we talked about how we can determine if a vector field is conservative. That is, how to determine if a vector field is a gradient field. That is, how to determine if a vector field has a potential function. That's the whole list. We want to determine we want to know how to determine if a vector field if a vector field is conservative. That is, the vector field is a gradient field. That is, the vector field is the gradient of some potential function f. And with f this way, that would mean that f1 is little fx and f2 is little fy. So in the setup that we have here, we're trying to determine if f1 is the derivative with respect to x and f2 is the derivative with respect to y. Rather than trying to integrate our way into a potential function, we can look at the mixed second partials to determine if f1 and f2 are the first partial derivatives. So that's our strategy. So if the partial of f1 with respect to y which would be fxy, and the partial of f2 with respect to x, that would be fyx. If we look at these derivatives, that will tell us if these two derivatives from our vector field, of the components of our vector field, if those two are equal, then f is conservative. Because if these two are equal, that means f1 was the derivative with respect to x, and f2 was the derivative with respect to y of some potential function f. So if the mixed partials are equal, then we can follow our mixed second partials up to the gradient, up to the potential function. So if the partial of f1 with respect to y is equal to the partial at f2 with respect to x, then these two mixed partial derivatives are equal. And that means the f1 is little f with respect to x, and F2 is little f with respect to y. And therefore, the vector field is the gradient of little f. Therefore, f is conservative, or is a gradient field. Therefore, f is conservative, and therefore, the fundamental theorem of calculus for line integrals applies. So once f is the gradient of f, we can conclude f is conservative. Therefore, the fundamental theorem of calculus for line integrals applies. So that's the setup. That's why we look at these partial derivatives of the vector field. So for example, let's suppose that we have a vector field is 2xy I plus xy times j. So f1 is 2xy and f2 is xy. So the question is f a conservative vector field? That is f1 the derivative with respect to x, while f2 the derivative with respect to y of some potential function f. Rather than try to integrate these two functions, even though we're going to do that after we check the second partials, we're going to see if the second partial, the mixed second partials match. So the partial of f1 with respect to y so the derivative of 2xy with respect to y is 2x. And the partial of f2 with respect to x is y. These two are not equal. Therefore, this vector field is not conservative. It is not the gradient of some potential function. We reach the same conclusion if we try to integrate. So we could look at f1 and we could say is 2xy the derivative with respect to x. So we'll integrate with respect to x. So if fx is 2xy, then f will have to be, we'll integrate with respect to x, and x squared y plus some function of y. Then if f2 is the derivative with respect to y, is if fy is equal to xy, we'll integrate with respect to y. That would mean f would have to be 1/2 xy squared plus some function of x. So notice that the terms that don't match in this version of f, I have an x squared y. And in this other version of f, I have a 1/2 xy squared. The terms that don't match are not just functions of one variable or the other. I have to have x squared y plus some function of just y. And that's not what we have over here. This 1/2 xy squared, the thing that doesn't match, is not going to be able to go in for my g of xy. Similarly, if xy is the partial with respect to y, I have to have a 1/2 xy squared plus some function of just x. But the thing that doesn't match over here is an x squared y, not just a function of x. So I cannot make an 1f out of these two functions. Therefore, f is not a gradient field. Therefore, f is not conservative. Therefore, fundamental theorem of calculus for line integrals does not apply. Therefore, we can't use the fundamental theorem of calculus for line integrals if we had to do a line integral around this vector field, or integrate this vector field over some curve. The fundamental theorem of calculus for line integrals says the integral of the gradient of a function dot dr is that function at the end point minus that function at the starting point. And we cannot make that function. There is no such f that has 2xy for a first partial with respect to x and xy with the first partial as a first partial with respect to y. Any questions? So this partial at f1 with respect to y equals a partial at f2 with respect to x is an important thing, important enough that we give it a name. So I'm going to grab this. And these two terms, the relationship between these two terms is what's telling us whether our vector field is conservative or not. So I want to summarize this piece of information. So we're going to define what we call the scalar curl. The scalar curl of f, a vector field f, which is f1i plus f2j. The scalar curl of a vector field is the partial at f2 with respect to x minus the partial at f1 with respect to y. If the partial at f2 with respect to x is equal to the partial at f1 with respect to y, that would make the scalar curl equal to 0. So if the scalar curl of a vector field is equal to 0, then the vector field is conservative. If the scalar curl of a vector field is equal to 0, then the vector field is conserved. Any questions? This has been very mechanical up to this point. Talking about conservative vector fields, talking about these scalar curl business. This has all been set up through mechanics. Here's the mechanics that we've been using to set up. Said if there's some potential function, then this gradient is a vector field. This vector field, the gradient, is made up of partial derivatives, and we can determine if we had started with this potential function, then when we get down to these mixed second partials, that scalar curl is going to be equal to 0. So if we had started with some potential function, then this is where we end up. The game that we're playing now is we're starting with a vector field. So we're starting here in the middle and saying, well, here we are in the middle. Is there some function up here? Because we have a gradient field, and we can check that through the scalar curl. The scalar curl of the vector field, the mixed second partials of a potential function. So mechanically, that's how everything lines up. Any questions on mechanically how everything lines up? How's everybody, okay? It's hard to tell. I've discovered that in a Zoom class. Normally, like in a class where everybody's here, you just have like that blank stare coming at you. Like copy and paste blank stare. But in Zoom, it's different. So in Zoom, it just looks like a bunch of names. Yes, there are. I'm sure there are blank stares on the other side as well. If there isn't a blank stare on the other side, it's because there's no one behind the camera. They're out making breakfast or getting more coffee. They just kind of like logged in and said, oh, I'm here. I'm here. Turn the volume up, go make breakfast. Not a complaint, by the way, that people are on Zoom. I would rather you be on Zoom than just bailing on the class. You know what I mean? So if we have a vector field, we're looking at a vector field, we can check the scalar curl to see if it is conservative. If the vector field is conservative, then we can use the fundamental theorem of calculus to evaluate our line integral. If not, then we have to do something else. Either just calculate the line integral, because that wasn't that hard. But let's see where we're at. We have a fundamental theorem of calculus for line integrals. I'm just going to put in the F prime version of things. I said I was going to put in the F prime version of that. So here's our fundamental theorem of calculus for line integrals. This is what we could do when we have a line integral of a conservative vector field. What if we have a line integral of a not conservative vector field? Do we have some theorem that kind of applies do we have some theorem that applies to line integrals of non-conservative vector fields? This was actually by complete accident that I wrote this one in green, because the theorem that we have here is green theorem. What a happy accident. Although I should spell Green's theorem correctly. So Green's theorem is going to be a theorem about line integrals. We're going to find the line integral of some vector field .dr. In this case, the vector field need not be conservative. This is just a theorem, but there's a restriction on C. C is going to be the positively oriented boundary of some region R. So there's something that we have to think about. C is the positively oriented boundary of a region R. So that means we're going to have a closed curve that will encompass some region. This says positively oriented. Remember that a curve, when we parameterize a curve, that curve has direction. So we have to have positive orientation, because this curve can travel this way around the region, or the curve can travel the other way around the region. So positive orientation means as we go around the region is on our left. So for positive orientation, the region will be on our left as we go around. This is a more generic way of saying counterclockwise. Counterclockwise kind of indicates there's some roundness to it, so we had to kind of genericify our counterclockwise. So the positive orientation means the region is on our left as we go around. So squished counterclockwise. So Green's theorem says if you're doing this line integral, doing the line integral of this vector field dot dr around some closed curve, this is equal to the double integral over the region of the scalar curl. So Green's theorem states that if we have the line, if we calculate the line integral around the boundary of some region, the line integral of some vector field around the boundary of a region, this will be the same as if we calculate the double integral over the region of the scalar curl of the vector field. Originally, I had set this up as some kind of theorem about line integrals that applies to non-conservative vector fields. This does apply to conservative vector fields, but kind of in a stupid way. If f is conservative and we're integrating over a closed curve, then p and q are the same point. So if f is conservative, we could just evaluate the potential function at q, then the potential function at q, and subtract those, and we would come up with 0. Also, if our vector field is conservative, then the scalar curl is equal to 0. So we would be evaluating over the region 0 times dA. So we get 0 in both cases. So it still applies if f is conservative. It just tells us that 0 equals 0. If f is conservative, then Green's theorem just tells us that 0 is equal to 0. Not exactly great revelation. One last kind of structural thing that we want to point out, that we're gonna take a step back and look at things from a great distance. Oh my gosh. I'm having trouble with my big F's and little F's. So we're going to look at this structure. It was easy to see that the when we had the fundamental theorem of calculus, the integral of f prime over an interval is the function at the boundary. The integral of the gradient along some curve is the potential function at the boundary. Notice the relationship between the thing that we're integrating and where we're evaluating at the boundary. It's kind of like we have the integral over some set. We have the integral over some set of something standing in for a derivative. And we calculate the integral over this set of the derivative of the function by evaluating the function at the boundary. The integral over some set of something that identifies as that we can identify as a derivative. It's like evaluating the function at the boundary of the set. So that region, we evaluate the double integral from Green's theorem is evaluating the scalar curl of the vector field over some region. And we can get there by evaluating the vector field itself at the boundary of that region. That's kind of the structure that we're seeing. The integral over a set of something that we can identify as a derivative is like evaluating the function at the boundary of the set. We've got two more fundamental theorems of calculus that are going to follow this kind of structure. We're going to integrate something that's like a derivative by evaluating the function at the boundary. All right. That's not something that you want to think about too much. You want that running in the background. We just want that running in the background. Integrating over a set some derivative, you evaluate the function at the boundary. That's what we had back in our fundamental theorem of calculus. That's what we have in our fundamental theorem of calculus for line integrals. That's what we see going on in Green's theorem. Integrate some derivative over a set by evaluating the function at the boundary. That's got to do it for today. I will see y'all on Monday, since tomorrow is a holiday. Everybody have a good long weekend, and thanks for playing.